Good morning, everyone. So it's 10 o'clock. It's time to start a new webinar session. So welcome. And today we will have, again, a session made by two parts. The first one will be about DetNet and the second one about ISAC. But first of all, a couple of informations. So my name is Andrea D'Aquino. I'm the chair of the Working Group 4 of 5G-ACIA. And let's move to housekeeping information. So the sessions will be two again. They will be about 20 minutes each, and there will be some time for question and answer at the end of those two sessions. Not at the end of each one, but at the end of the entire webinar. Should any question remain unanswered, of course, you can contact us to become a member and get it answered. We will record this session, and the recording will be made available afterward on our website. And should you encounter any problem, then please write in the chat, and you can use for questions both the chat and question and answer window in Teams. That being said, everybody is muted by default. Of course, that being said, let me start by presenting you the first speaker. That will be Marilet de Andrade Jotim, who is a master researcher at Ericsson. Marilet, the stage is yours.
Thank you. All right. So, welcome to this web seminar on DetNet-based deterministic IP communications over a 5G network for industrial applications. So let's see a little bit of an agenda here. This content is based on the 5G-ACIA white paper here, and the results are based on the work where we wanted to explore the question on, can DetNet over 5G be useful for industrial applications? And to answer this, I will first provide a brief overview of deterministic networking, DetNet, and what is the relation with time-sensitive networking, TSN. Then I'll discuss how DetNet is supported by 3GPP 5G, and I'll continue by showing use cases that might benefit from DetNet given their characteristics and needs. And finally, we will look into some examples for the DetNet 5G industrial deployment scenarios. So let's start. What is DetNet? Well, DetNet is an IETF standard that is able to deliver data flows with extremely low loss and bounded latency. It has, to support that, it has different planes where it works. It has a data plane, which is based on IP. It's a layer 3 data plane. And it may also be based on MPLS, but in this presentation, we're going to focus on IP. And it has also a controller plane where it can have many configurations, but in this case, we use the centralized configuration, and therefore we have a DetNet controller, which will be in charge of configuring and maintaining the DetNet flows. And basically, DetNet is like a kind of upgrade for a DetNet, any router, let's say. And it only applies to a single administrative domain. From DetNet, we can, it's a very wide technology, but in this presentation, we're going to highlight a couple of features that we consider the most important. The first one is explicit routes. It is like a dedicated path, and the resources are reserved for this path. This path has the particularity that is not affected by changes due to convergence of routing protocols. So it's quite stable. And then we have the second feature, pre-auth, which stands for packet replication, elimination, and ordering functions. It is a feature that uses the explicit routes to make a kind of per packet redundancy. How? Well, it uses two or more of these explicit routes or paths that are disjoint, and it will replicate every single packet over every path at the ingress node of the DetNet domain, and then at the egress node of the DetNet domain, it will eliminate the replicas and it will perform any needed ordering of the packets. So in this way, for example, if a packet is lost, then the other replica in the other path will work, will still be there. So this makes a good solution for protecting the packets and minimizing the packet loss. And there are different types of nodes in DetNet. It's long to explain, but I would say that if the node supports both features, then these nodes are called either edge or relay nodes. If the node supports only explicit routes, then it is a transit DetNet node. Just for your information, we'll see later. So let's continue. Then we know that in industrial automation, time-sensitive networking, TSN, is an important technology. And that is why we have investigated its relation with DetNet here. DetNet and TSN have similar objectives, but are applied at different layers. TSN is defined by IETF, and it's an Ethernet-based layer 2 technology offering time-sensitive communications, while DetNet has the same purpose, but it is applied at layer 3. It's a layer 3 technology. So first, let's note that by means of a layer 3 data plane, DetNet has the capability of interconnecting layer 2 segments. So this is very important. And those segments could be, for example, TSN segments. Indeed, interoperation between DetNet and TSN is possible in two main scenarios. One in which TSN is barely a sub-network of an end-to-end DetNet network, and another in which DetNet is used to interconnect two separated TSN segments, for example. And these have been defined in IETF as possibilities. So interoperability is also standardized. It's important to note that most of the features of TSN are also supported in DetNet. This includes traffic shapers such as QBV, those who know, and this is done by leveraging queuing techniques that has been defined in IETF. So let's look at 3GPP. In 5G, DetNet is supported from the 3GPP release 18. The idea here was to define the 5G system as a logical DetNet node. To do so, changes were proposed at the control plane and at the user plane of the 5G system. So it's like a black box that will look to the outside like a DetNet node. And then we have defined ports in the user plane, and it really looks like a router, right? And how we do that? Well, in the control plane, there is a function called TSF, time-sensitive communications and time synchronization function. And this is reused to interface with the DetNet controller. And there are protocols and young models to be exchanged here. And then the TSF will configure, will get information from this DetNet controller. They will exchange information. For example, what are the characteristics of this router? What are the ports? What's the IP address? And the DetNet controller then, after making calculations, will configure all the routes in the path for a DetNet flow. And the TSC-TSF will receive this information and it will map all these parameters into a configuration that is valid for the 5G system. And then it will be transferred to the user plane. So here in the user plane, there's barely no need to do much because it's IP-based. And so basically, we need to use network side TT and WTT at the UPF, which is the user plane function. And here it's basically in case you need to report the ports, the number of ports. Here you're allowed to have multiple ports, and you can connect to a DetNet network. At the UE side, the user equipment side, we have a single interface with a DetNet system. It can be a end host or it can be a root. So as per release 18, the 5G DetNet node only supports explicit routes. It doesn't support pre-auth. Therefore, this is a transit node. Then the 5G industrial automation use cases have been analyzed for different DetNet applicability to see if it is a potential solution. And some markers have been highlighted for the suitability in IP communication. For example, the span area, if they are IP-capable devices, if there's a need for interconnection with subnetworks, and the edge clouds. And all these use cases have been noted as possible potential use cases that can benefit from DetNet. So here they are listed. And in the next slides, we will show a couple of use case examples. Here we have a flexible modular production use case example. This is within the factory automation. There are multiple types of zones that can be added, for example, seamlessly. So that's why it's modular. Zone A is a larger area with flexible production and logistics. And Zone B is like a modular cell, like for production cells. And some appliances will stay within a cell, for example, in zone type B, and others will be moving around between zones. So here we have a large span area with multiple subnetworks per zone. And there's a need also to communicate between zones, and there is a need to communicate between mobile assets. So this is the best scenario for applying DetNet. In this example, also self-organized networks are required, and these are usually implemented using IP-capable devices. So then again, this is a good case where DetNet over 5G can cover the needs of large span communication, mobility, interconnection of subnetworks, and especially when the devices are IP-capable, but not limited to that. And we have another example. Here we have virtualized industrial functions. In this example, there is a virtualized industrial function in the factory data center or the edge cloud. And this virtualized industrial function can be, for example, an industrial controller that will control those appliances in the factory field. And so it is required to have a deterministic communication between this edge cloud and the field devices. And also we see that there's different subnetworks required at the field level. So We have multiple subnetworks that need to be interconnected with a virtualized or multiple virtualized industrial controllers. So again, a deterministic network infrastructure will be the best case here. And there are more use cases and examples that you can look at the white paper if you are interested. Now here, let's look at the industrial deployment scenarios. In this case, we have explored how DetNet could be deployed in 5G industrial applications. To do so, we look into two cases, a pure DetNet or greenfield DetNet, or in combination with TSN. So in the pure DetNet, we may have 5G DetNet router at the backbone. We can also have it at the production cell, at the field level. The control may be local, or it may be, as I mentioned before, at the edge cloud. Then we also have a combination with TSN, where DetNet, 5G DetNet router can be part of the backbone. And TSN is usually deployed at the field level. It's usually where you use the layer 2 technology. And then another option would be that you simply have a 5G TSN bridge at the production cells, and you have a DetNet-based backbone. So these cases are possible. I'm going to show two examples. In the first example, this is a pure DetNet case, where DetNet is both at the backbone and the production cells. There is a local control in this case, where the DetNet controller is located, and we also have may have some controller functions there, especially if it is an edge cloud. And the appliances at the production cell will connect to the network via the UE, the user equipment of the 5G system. And then the 5G system will be a DetNet node that will interconnect with the centralized control, and will also interconnect between subnetworks, between production cell 1 and production cell 2. So with 5G DetNet node, we facilitate the wireless deployment and seamless connectivity with and between appliances within the production cell, with the centralized industrial controller, and between the production cells. Then we have a second example. In this case, we have a combination with TSN. And as I said, TSN is the green boxes here, is deployed at the production cell. Here we have, in this example, that the 5G is used as a TSN node or bridge, and it will be interconnecting with the production cell devices. Here there's something different. We have these blue boxes. They are what we call the edge DetNet nodes, and DetNet edge nodes are used to interconnect or with DetNet unaware devices or networks. And this is located at the edge of the DetNet domain. So, but as we know, 5G is just a type of transit node. It cannot be, for now, an edge node. So therefore, placing a 5G in this in this situation will not be possible, but it will be possible as a transit node in the backbone. And with this, I have reached the end of my presentation. I will give some recap here. So we have shown that deterministic networking is a promising IP-based technology specified by IETF. It is supported in 3GPP Release 18. It has a large applicability in 5G industrial use cases, and there are different deployment scenarios where DetNet and 5G can be applied by either using pure DetNet or in combination with TSM. And the key highlights, I would say, are that for the great majority, DetNet appears as a promising option in terms of fulfilling the requirements, And this can be requirements of latency, but it can also be requirements of interconnectivity with large span, with larger areas, with interconnection of networks, using IP-based devices that can interconnect, for example, with an edge cloud. And this is all from my side. Thank you so much, and see you later for the next questions.
Thank you, Marilet. So we come to our next session by Hanwen Cao. Hanwen, are you able to share the slides, or maybe the office can do?
Hello, everyone. So yes, I can share the slides.
Very good.
All right. Let me. Window. Okay. Presentations. Window. All right. Good. Can you see my screen?
Yes.
Okay. Excellent. So, hello, everyone. So I'm Hanwen Cao from Huawei Munich Research Center. So it's my pleasure to present you the white paper of 5G-ACIA on the use case and requirements for the integrated sensing and communication for the connected industries and automation. So if we look at the let's say the further target of IMT 2030, we will see some new features appears. So as you can see from this, I would say, kind of well-known picture that in IMT 2020, we work on eMBB, MMTC, and URLC, and it's further extended to the 3 new features, including the integrated sensing and communication, which is the topic of the today. Yeah, we can also interpret and this will further extended and enhanced with high performances. But the new features, including sensing, including AI, ML, and also the global connectivity, is something new. So this is, I would say, a brand new feature for the 3GPP system, because in the history, in the 3GPP network, in 2G, 3G, 4G, 5G, we mostly talk about the data connectivity in a mobile wireless scenario. But it is the first time that we are talking about some features rather than communications. That is sensing, yeah. What is the so-called integrated sensing and communication, ISAC? So it is targeted for using the same cellular network infrastructure to provide both wireless communication and sensing services. That means it's going to be a unified network infrastructure, a unified usages of spectrum resources within the unified standard framework. There are many applications being envisioned by many studies, research, and even now starting standardization in 3GPP. So, which includes, let's say, detect tracking of objects, humans, detecting the human gestures, postures, even vital signs, to reconstruct the environment in 2D or 3D, do penetrative imaging, material sensing, micro movement, micro Doppler sensings, etc. So there are many has been considered from different bodies, including 5G-ACIA. I will talk about this later. And the key benefits is that by integrating the sensing and communication network, we are going to provide integrated and networked and coordinated systems, which will enable the multi-static, bistatic, monostatic, and even multi-view sensing. This is beneficial for sensing coverage and reliability performances. And also in 3GPP, it also considered to integrate, let's say, non-3GPP sensing, basically not radio frequency technology-based technology into the play. So with the multimodality, the sensing capability can be further, let's say, extended. And meanwhile, this is going to be a highly coordinated system. So different sensings are integrations for the smooth evolution of the technologies. So at the beginning, this could be application level sensings. So sensing and communication systems, they are relatively independent, separated, and they exchanging informations in the application level. And later, we can utilize the same spectrum, but with separated system for sensing and communications. This is also to can enable the evolution of the communication network more smoothly with a bit independence from the sensing features. And ultimately, we target for full integrations that the both sensing and communication features are integrated at all the levels and hardware, software of the whole, let's say, 3GPP network system. Okay, this is the technology overview of the system. So what are the state of the play of the ISAC technologies? So this is actually starting from the, let's say, the research community. There are already many works ongoing or has been done. For example, in the European Union funded SNS framework, there are several, let's say, large scale projects which has taken ISAC as a very important technology building blocks of the future wireless network. And also there are research organizations such as 16G, the IMT 2030 6G promotion group, also IEEE Communication Society. They have quite some active works on these technologies. And in the standardization level, we see that at ETSI, there's a dedicated specification group on the ISAC technologies. So they have, I would say they have achieved quite some also interesting work, releasing the white papers on the use cases of ISAC, also including the other work such as channel modeling and also system run architecture designs. Also for the IC terahertz technologies, they have numerous also ISAC use cases been defined in their report, the GR terahertz 001. At 3GPP level, so starting from release 19, there are study items on use cases of ISAC, study item on the service requirement of ISAC. So there are stable technical report and specification being released by 3GPP. Round 1 is working also on ISAC channel modeling. I think that work is pretty much close to be finished. And also the architectural study in SA2 has been started in March of this year. Also in the IEEE community, so using the wireless communication network of Wi-Fi for sensing has been even started earlier than the 3GPP. So this in 802.11bf, this actually have let's say approved specifications this year. And also, as aforementioned, that the IEEE Communication Society has also emerging technology initiatives on ISAC technologies. So from our 5G-ACIA, so we have started to investigate this new technology features starting in September 2023. And we have a great support from multiple members of 5G-ACIA in this work item on our website. So this webinar, we will give you a brief overview of the key findings in this white paper. And in this work, during this journey of this work, we have also quite active interaction with ISG, ISAC, terahertz, and also 3GPP. Yeah. So the benefits of ISAC for industrial automations. So a unified infrastructure. Of course, it's well known that for industrial automations, we widely use different type of sensors. But for ISAC, we try to, let's say, provide some of the sensing functionalities in a unified 3GPP network. So let's say for mobile network for industry environment, we can provide both communication and sensing within the same network infrastructure. That could be attractiveness of cost reductions. Yeah. With ISAC, it is hopefully can provide higher sensing performances. So we have, let's say, the nature of the wireless network. We have a multi-node, multi-static, multi-modality sensings. So this is a more comprehensive sensing solutions in comparison to some, let's say, single device-based sensing solutions. Also, we can utilize the wide range of radio spectrum for 3GPP networks for sensings. So this is also might be provide better, let's say, resolution occurrences for sensings. And because the wireless communication network is naturally designed for to function, to survive in an interfered environment with coordination. So this will also benefit sensings. Yeah. The suitabilities in the harsh environment. Mostly when we talk about ISAC, we'll talk about using the, let's say, the RF-based sensings. And this type of sensing is well suited for environment with dust, heat, humidity, and low light conditions. You can imagine how, let's say, for example, in the high temperature or dust environment, for example, sensors like camera or LiDAR, their glasses, lenses can be, let's say, very sensitive or very vulnerable in this environment. But for radio frequency-based sensings, let's say, antenna systems, they are much more simpler and could be more robust in such kind of environment. High data security, because it's highly unified and integrated, so we can rely on the strong 3GPP security mechanisms to provide, let's say, trusted environment for data transferring. And on the privacy protection aspect, so in some environment, you know, the, let's say, optical sensors like cameras, also things like microphones, they tentatively to over collect unnecessary informations. But the radio frequency based sensings naturally minimize this over data collection and can eliminate some of the privacy concerns. So from 5G-ACIA, we identify the following applications which are highly interested or relevant for industries. So the first one is detection and tracking of ground and aerial vehicles and also human beings. So this could be used for traffic monitoring, for optimize the production flows, and also for security aspect, it is a good means for intruder detection, for example. Tracking and measurement the size of goods. So this benefits for the, let's say, the production efficiencies and also for inventory management. Human machine and the machine to machine collaborations. So in some conditions, how to interact with nowadays more and more automated and even intelligence machine or robotic systems. So in some conditions, we can use gesture or posture sensings to sending signal to the machineries. When especially in conditions where humans are highly protected, we cannot easily operate things like, let's say, the control panel, etc. Yeah. Safety and healthy at work. So the RF sensing is capable of monitoring the vital signs of sensings and also to detect the dangerous scenario like a fall of human beings, but also while not using camera for over collecting privacy data. Yeah. Environment mapping. So we can use leverage on the, let's say, the RF sensing's penetrative capabilities to also to make a bit, let's say, beyond visual or a bit non-line of sight mapping And also we can also naturally, let's say, rely on the, let's say, the sensing mapping function of ISAC to also provide information for optimize the communication performance, for example, to eliminate the blind spots of communication network. Predictive maintenance, so some properties can be extracted from ISAC, like, for example, the micro Doppler aspect. We can extract information which indicates the health of machineries based on the vibration analysis and also the vibration of pipelines. So which could be a very, let's say, capable means for indicate potential maintenance requirement of machineries and pipelines in factory automation and process automation scenarios. Quality inspections, so with certain, for example, high frequency signal in radio frequency, we can use it to detect some potential defect of products, even penetrating the, let's say, the surface of the object of interest. Also, there could be also a potential that the localization and communication performances can be further improved using ISAC for providing some side informations assisting the localization and communication. Yeah. So this is a let's say the application aspect for industries what we're interested. Now let's go to some specific use cases. So this use case is that is particularly suitable that we can use ISAC to detect the gestures of human workers to interact with machineries in a touchless manner. Because in some industrial scenarios, the physical contact may be very restricted or cumbersome. For example, in some highly protected scenarios, when the human workers wearing gloves, and also the environment could be very noisy, so making, let's say, the let's say touch control or voice control very difficult. But using the ISAC, we can use the ongoing, let's say, data transmission signals to also to detect the human workers' gesture. This can be a good means for contactlessly control the machineries. Yeah, this is a means of enhancing also the accuracy. For example, could be an emergency stop, could be gesture can be detected by ISAC, and to avoid any collision of machinery to the human workers. The second use case is a vibration monitoring for industry environment. This is highly related to the maintenance aspect of the machineries, pipes, and even also the building structures, preventing potential damages and also improving the operation efficiencies. So there are vibrometers which are used for these purposes, but in some cases, let's say the contactless and wireless sensing is needed. With ISAC, we already have this, let's say, network wirelessly providing, let's say, data connectivities in the factory level. And meanwhile, we can use this type of RF signals to capture the micro movement or micro displacement of objects in the environment, which can provide add-on services that the vibrations of machineries or pipelines can be detected. For example, some certain unwanted harmonics is captured, which may indicate something is not working as expected in this industrial facilities. Yeah. Another use case is to also to use sensing to do the stockpile monitoring. So for stockpile monitoring, so the challenge is that it could be in a low light conditions, and it could be the area is very huge. And the stockpiles, so there are works, for example, to using, for example, radar technology for stock monitoring, But with ISAC, we can naturally, let's say, rely on a properly deployed, let's say, wireless nodes, G-Node B or user equipment type of devices to also provide let's say, the radio sensing informations for detecting the volumes, the height of stockpiles, for optimizing the inventory management and the production efficiency. The fourth use case is a bit larger picture of how to use ISAC to optimize the whole production flows. So this is there is a, let's say, production as a service concept proposed by our member company Trump. So the essential thinking is that we can have ubiquitous sensing functions at the factory facilities. So the movement of goods, the movement of human workers, and can be properly detected, which can provide, let's say, the high level of informations to identify potential bottlenecks or even risk in the production flow. Another case is focused on the safety aspect of industry environment, which is of crucial importance. Yeah, by relying on the RF sensing and also multimodality sensings, we can have integrated solutions to detect any hazardous conditions, like human falls, toxic gas leakages, which may require dedicated sensors integrated into the 3GPP system, and also to provide the in-time, let's say, alert to the responsibilities. In this case, let's say, a wholly integrated, let's say, sensing functionality to protect the human workers in the industry environment can be, let's say, implemented from the 3GPP network system. Okay, so we have given a lot of quite some, let's say, introduction of application and use cases of ISAC. So I would also like to share you some of the, let's say, the real world cases of how ISAC can help. So from our activities in research on these technologies. So as you can see here, we can, we can really do, let's say, high resolutions images from RF signals. As you can see here, we have an object which is made of metal sheet, and we can really use the very high millimeter wave frequency band to create a very fine resolutions in the space to give images or even penetrative images of the object of interest. So in this, let's say, research case, we implement a 3GPP based physical layer, and we can use some synthesized aperture technologies to really create a quite, let's say, a big aperture with a fine spatial resolution. You can see this 2030, which is images with, let's say, millimeter level of resolution. Yeah. Another case I want to share you is in a larger scale, how we can use the ISAC technology to, let's say, to detect and localize the objects and even to detect its shapes. Yeah, as you can see, this robots with different posture has been detected with a dot cloud and with, I would say, quite decent resolutions. Besides, on the right side, you can see we can give also a 3D point cloud generation of the whole environment. We can identify a moving object. This is an AGV carrying a box, and this is also a corner reflector as a reference. So we can really see the 3D world with, let's say, decent resolutions with ISAC, also in the near field scenarios. And yeah, in the third case, we can see that the three objects, their locations in 3D are detected and differentiated. So which indicates a good potential that we can use the, let's say, the 3GPP, let's say, compatible technologies to do high resolution sensing. Another case is that how to use the micro Doppler, that's the Doppler aspect of the radio frequency signal to do the sensing. For example, you can see here my gestures are captured with the signal, so we can generate, for example, the Doppler feature. In this case, it's going to be a Doppler time feature for the sensing, and this different gestures can be interpreted as certain instructions to the robots for control its movement. As you can see in the background, we're also using 3GPP compatible waveforms. In this case, it's basically OFDM with 16 QAM modulations. Yeah, that's all of the, let's say, I want to share with you about ISAC for industries, which has been funded by 5G-ACIA. So some key takeaways I want to wrap up and share to you is that it's going to be a emerging, let's say important emerging capability of the beyond 5G wireless network, and also it's going to be further, let's say, developed in the 6G era. So currently there are many people working on it, and of course it's still at its beginning phase, but we see it's a high potential. Yeah. Second, we view that ISAC has considerable potentials to advance the efficiency, quality, flexibility, and safety, and also information security and cost optimizations for our connected industries. We also believe that now everybody is talking about AI, using AI massively. So leveraging the power of AI, I would say the integration of sensing and communication may be unleashed with even greater potential to open up new applications, new businesses. Yeah. So integration is the key that which has been envisioned 2,000 years ago by Aristotle. The whole is greater than the sum of its parts. So we are entering the era that the wireless mobile network will run far beyond the wireless data connectivity, but fully integrated infrastructure with communication, with sensing, and with intelligence, let's say massive integrated. Yeah, that's being excited. Yeah. Okay, thank you very much. This is all my talk.
Okay, thank you very much, Anwen. And I do have already some questions. I'm currently exploring the Q&A panel. So there is one from Uwe. Which activities are going in China and US regarding ISAC? You know, if anything is going on towards standardization, funding projects, government projects, etc. The question would be for Wen.
Okay, I think so. Thanks, Wu, for the question. Yeah. Anyway, I would say, let's say, my observation is that the let's say US side, I cannot answer much because we don't have business there. But of course, for the research, we have some observations. So also from China side, so I would say the China side is very active promoting the, let's say, the 3GPP technology into the next generations. So now, of course, people are starting to let's say to talk more about it. It's a 6G, and I would say ISAC is going to be, let's say, the one now of the three most important new features, as I presented in the first slide, that it's one of the new three features in the evolution of 3GPP's technologies towards IMT 2030 framework. So I guess nationwide, of course, they are let's say national rounding research program on this, yeah, I would say it's quite active. Yeah, as well. I would say.
Okay, then there is yet another question from Thomas. Is ISAC depending on a 3GPP release? And if yes, beginning from which release will it be supported?
I would say it starts in release 19, right? So the use cases and the, let's say, service requirement specification has already been done starting from release 19. Now the release 20 is has been opened up. I would say we could see quite substantial, let's say, specification of technology of ISAC even in release 20. So that is starting now. So because that's the details design of in the radio access network, also in the system architecture aspect. So I would say, at least from a standard perspective, we could envision that release 20 will release the first wave of let's say the functioning ISAC features. Yeah.
Okay, thank you very much. And I see no other questions. Let me go back to the Q&A panel. I see no other questions. So I have one, since we have a few more minutes to spend. So it's about DetNet and DetNet plus TSN. So Marile, would you give a couple of examples of two use cases, one for the DetNet and one for the DetNet plus TSN, or at least the most successful ones that you see?
Yes, thank you for the question. If you go to slide 10. Yes. So for DetNet combined with TSN, I would say in factory automation, here we see motion control. This is very tight. It has very tight requirements, and it usually requires TSN for certain cases, but then it can be combined with DetNet for interconnection of the sub-networks and for interconnection with a controller that is at the edge and so on. So this could be an example, but absolutely all the cases could be applied with TSN and DetNet together. This is one answer. The other answer, DetNet alone. It also, we have found that since DetNet can cover most, if not all, the features of TSN, then DetNet can be easily applied to all the use cases. For example, when it comes to mobile robots on cooperating carrying, and those examples that I presented in slide 11 and 12. Those are perfect examples for DetNet by itself, especially when devices need a connectivity with a cloud, edge cloud, that is IP-based. And also in scenarios like this one you're showing, where devices are self-organizing and usually required to be IP-based. So then the direct option is DetNet. There's also other use cases. There's when the industrial protocol that is used in the field is IP-based. So there's a number of industrial protocols used that will define what do you want to use. This would be my answer to the question. I hope I did well.
Thank you. Again, I am just checking the fields. Okay, it looks like there's no more questions. So thanks everybody for the time, and thanks of course to the presenters for presenting. Again, please, if you have any more questions that you hadn't the chance to ask, then contact us on the email that were presented in the beginning, or you can find again the registration of this webinar on our website, but also of course there's a LinkedIn that you can go and explore to get in touch with 5G-ACIA. Thanks again, and until the next webinar.